Welcome to Module 8. The Module 8 will demonstrate the RCM case studies, and in this module we use the same example that we used on the day one of this training. That means the pump, the compressor, and the tank. But here we use some information from the FIMEA, but focus on RCM. That means demonstrate how is simple the RCM methodology, as we already demonstrated in Model 2. But here we intensify and put more case studies and applying the case studies that we defined the day one. Okay, so again, the RCM is applied for different system and equipment. As we already discussed, one of the main challenge is sometimes to find which are the equipment that's in a complex system such as this platform. We starting our RCM, and for that we have, of course, criticality analysis, as demonstrated before in the previous model, that will give you a hierarchy of RCM implementation. And of course, in some cases, it's very clear which are equipment that have low performance and where the maintenance tasks need to be reviewed. Okay, so let's go to our first case study. That's the pump, centrifugal pump. The first step of the RCM, of course, after to define the hierarchy, the list of equipment that needs to have, that will be the RCM scope. We need also to consider the components that will be under the scope of the RCM. So in case of pump, we are considering the seal, bearing, impeller, the case, the pack, and the shaft, the nozzle, and the coupling. So it's very important to have the list of equipment in order to have clear which are the components scope during the RCM. And the RCM is very important to do in components level, and also consider the failure modes, because we will be very clear the specific maintenance task that need to be carried out for in order to detect the equipment damage and deterioration and avoid such failure happen. Okay. Again, we have different source of information in a process plant in our organization, and ideally we would have a FRACA system that integrates all the information, or even a set management system that integrates all information concerning equipment failures and also preventive maintenance that's already in place. But in many cases, the different maintenance group have equipment files, and that we can find in most of the company. And these files in some cases are not electronic source, they are in papers. It's not a big issue as well. We need to sit in there and look on this equipment historical of the failures that happen, and the technician operators that will be part on the RCM workshop need to bring such information in order to give some inputs and also justify their recommendation concerning maintenance tasks to the group. Okay, so in this type of templates, of course, we have the dates, that's the failure war capture. We have the equipment tag here, we have the group, the technician, the specialist, maintenance specialist that's carry out such maintenance. That's the type of maintenance corrective, when that failure happens, when starting the service, when finish the service. Such type of information is very important for reliability engineer that carry out lifetime data analysis in order to predict the equipment reliability as well as the maintainability. So as we already discussed in some models before, in some cases, modeling the system is very important in order to check the effects of such preventive maintenance in the asset performance in a system level, or even as well the impact of preventive maintenance on life cycle costs of the equipment or in the system, and the impact of life cycle costs by defining the spare parts. So of course, many maintenance engineer, technician, and operators are not reliability engineers, but they get such input information from the reliability engineers and work together with them to model and demonstrate the impact of the preventive maintenance definition defined during the RCM in system performance, in life cycle cost, as well as in spare parts cost. Okay, so in this is they need to have some files, some source of information to do that, and that's a demonstration in case of the pump. So we have different components here. We do not have the failure mode described in here, but it's already a first step. So of course, in the root cause will be described the failure mode, and we can also have a picture of the equipment here. Okay, so let's take a look on a FEMEA of the pump, and one of the first steps that we have in a FEMEA is the equipment definition and the equipment number. So here we can see in this FEMEA template, that is the input for the RCM, that we have defined the leaders, the documents, the dates, the plan, the system, subsystem, and the equipment. Okay, so we have a pump that has a standby one is a centrifugal point pump. We have a two with 100 capacity, so we can see that we have one standby. Here are the function of the pump, and here are the function defined for each components of the pump. Okay, so we need to define the risk matrix that we will use during the FEMEA. We are already discussing that. So an example that we are going to see in our FEMEA is, as well as a RCM, that's a unique template, is this risk matrix combination. So you can see the combination of we are going to see the combination of severity category with the frequency, and different colors that represent no tolerable risk, moderate risk, and tolerable risk. Okay, so let's go to the first example of our pump RCM. So as I mentioned before, we have an integrated template that we have some information of the FEMEA as well as the RCM. So since we carry out the FEMEA, what we're looking here, what we're looking for as RCM inputs are the failure modes that have as a recommendation preventive maintenance. Okay, so based on these failure modes here, for example, we can see the sizing that is triggered by high vibration, and during the FEMEA the recommendation was to define preventive maintenance in order to mitigate the risk. During the RCM we discussed that, and for this specific case we decide that we need to have vibration monitoring online, or vibration analysis that as a predictive maintenance. Okay, so we can have a vibration monitoring online to detect the high level of vibration when achieve the threshold or vibration that can trigger some sizing in the bearing. So and that's the main RCM task. So and that's clear when we define some task here, what kind of problem, failure modes, and we want to avoid, and how we are going to detect what is the cause that triggers our failure modes we are trying to detect. So we can see that the sizing can have different causes, and such as insufficient lubrication or contamination of lubrication, that will probably request different types of action. So here, of course, the main issue is to have some procedure and follow up the lubrication procedures to avoid sizing, but concerning vibration, we have totally different recommendation. So here again, when we have all failure modes, we can also check if there is necessary, even though we do not have non-tolerable risk level, if we need to apply some preventive maintenance tax. It's not prohibited that we, in this case, we put in here some routine to check the lubricant quality. Okay, the main point is we need to be aware that after the RCM, similar to the FEMEA, the managers will review and approve all the maintenance tasks, and that will be limited to some budgets. And in some cases, one of the most important information is the level of the risk that the preventive maintenance is mitigated. So in case of moderate risk or tolerable risk, of course, that will be not the priority comparing to the non-tolerable risk that's mitigated for a maintenance action. But it's not prohibited to look on the other failure modes and put some preventive maintenance task here, okay? Let's move forward. So in the bearing, you have also other failure modes such as cracking and worn out. Both that are caused by vibration will be mitigated or avoided by this vibration, monitoring vibration. That's a preventive and that will be online, okay? So here we can see also that's another type of root cause that trigger bearing worn out is the contamination on a lubricant. In this case, we monitor the lubricant quality and check this quality online, and that's as a system online. And again, the system online can be more expensive than that's the routine of checking. And then, of course, there will be a discussion about that, and in order to check if the budget is enough to encompass such task. That can be some modification, the type of the task. Again, that's the manager can questioning that, and then we need to review the RCM reports. In the end, we have with all the RCM with the final recommendation, and that need to be in the recommendation and the maintenance tax that need to be in the system. Okay, so let's move forward and take a look on the seal. And in the seal, what we already have here as critical failure mode is the erosion, and that's the cause of the erosion is flush fluid contaminated with abrasive particles. So we need to have some sample fluid analysis, and that we do every year. So that was the task defined during the RCM by the RCM group concerning seal. So here we have other critical issues. So during the RCM, during the FMA already was defined. For example, one of the cause of the seal worn out is wrong installation, and during the RCM was established that there need to be a pump or seal installation procedure. So it's not necessary to repeating here because that will be the same action. Okay, but this one is already monitoring by the female leaders. So in some cases we have the same leader. So this Dr. Eduardo Calixto is the one that will monitor such actions defined during the female or RCM. But in some cases we have different leaders, and in different leaders we monitor different actions and mitigate actions. Okay. Another issue, a critical issue for surface corrosion, that's caused for chemical attack doing wrong materials. So that's a type of design mistake. So here the phase is the design, and of course we need to carry out design and review in order to mitigate this risk. So it's not a scope of the RCM. And let's move forward. Here we have another failure mode such as seal cracking and seal faces. So in some cases, some not in here. In some cases, the proposal check will mitigate some issues in also in other failure modes. So here we do not input any maintenance task in our RCM because it's not a request by any mitigate actions regarding preventive maintenance. Let's move forward. Now we're changing for packing in nozzle. So packing, the big issue here is the gland loose, and that's caused by vibration. And again, we have vibration monitoring online to avoid this gland loose in a pack, this failure modes. The nozzle has no any particular recommendation from the RCM, and the O-ring as well do not have any particular recommendation because the failures are not considered critical. But again, I can implement as much as recommendation I want in here. And in particular case when we do not have the FMEA, that's happened because the maintenance specialists, they will usually try to implement many recommendations to avoid the problems that you already know, and to mitigate that, of course. And in many, but in some, that's happened in many cases. That's such kind of number of recruitment days is quite high, and that's impacting life cycle costs and do not necessarily bring the system to a high performance level, but increase the operational cost. So we need to avoid that. Whenever we have the FIMEA, that's as input for RCM, this information is very clear, and you really need to justify why you having a task if it's not necessary to mitigate that's not mitigate the risk, and you need to justify that, and the manager cannot approve. That's clear when you have this type of methodology. Okay, let's move forward. Now we have casing again. No, there's no any let's say critical risk here that need to be mitigated for preventive maintenance. When we have the impeller, in impeller we have wornouts. The wornouts main issue is excessive solid in fluid cause premature wear out. So that's a big issue for the impellers. And then we need to have again the sample fluid analysis similar that we have before for every year. Okay. Concerning the shaft, in this template we have a lot of non-tolerable risk here defined during the FIMEA, and we in the first case here, for example, for worn out in the shaft caused by this excessive solid in the fluids, we have this same sample fluid analysis, and we need to start. We can also have worn out in the shaft for wrong installation, that's during the commissioning. So we need to have installation procedure, but as well here vibration test after installation in order to check that the shaft was installed properly, and the level of vibration is the level of vibration defined during the design specification. Okay, we can also have a fracture for again for excessive vibration, and here we, as a recommendation of the RCM, have a monitoring vibration analysis online, and for the corrosion, that was a chemical attack caused by wrong specification. So that's a design issue. So let's just request a design review. Okay, so that was the case one. Let's move to the RCM case two, similar that we had in the FIMEA, but focus on maintenance. So again, we need to, in case of compressor, that have a lot of boundary system that support this part of the, let's say, the compressor system. We need to define the scope of an house. Okay, during the design, of course, all of the system will be the scope. We need to prioritize which one are more critical, but during operation, maybe all the boundary system are working properly, have achieving their index, perform index, and we need to focus on the compressor. But that needs to be defined on a list of equipment. In our case study, we define in this such equipment such as seal, bearing, impeller, case, packing, shaft, nozzle, coupling, control units, valves, and filters, as well as lubricant, oil, and units and blades are the components that are under the RCM scope. Okay, and of course, as we discussed before, at some point we need to model such impacts of such preventive maintenance in performance, spare parts level, and a life cycle cost, and then we need to get the same structure in our RBD model. So it's like an example of a list that is starting to be built to build an RBD. Okay, so let's take a look on the FIMEA again. So we have the same template in here with similar information that we have system leader of the FIMEA. So during the FIMEA was defined the equipment. Again, we have two compressor, one standby. You can check here in this configuration, 2 plus 100%. We have a centrifugal compressor. We define the function in this part of template here, and for each one of the components we define such a specific function. Okay, so here we have also the other components with their defined equipment description, the configuration, the function. So let's go to some compressor parts. Do not focus too much on the parts that we already discussed in the pump. So let's see what we have as a new. So the blade, for example, is one of the critical parts of the compressor and the turbine, and we need to pay attention on critical issues. So during the female, we define that we have a critical issue for the failure modes worn out, and that's the excessive solid in fluid cause premature wear out. Okay, so for this case, we need to monitoring the product quality, and concerning corrosion. Contaminated fluids can cause corrosion, so we need to define some preventive maintenance and monitor vibration online here to that's not applied for this case. That's a mistake. In the case of contaminated fluids, we need also to monitor the product quality. So the vibration is related to here the cracking. So in case of high vibration, we need to define the monitoring online for this high vibration. Okay, so this one will be similar to this one here, need to be reviewed. Let's see another component. So another system that's important for the compressor is this the so-called safety integrity safety instrument function. And safety instrument function has the objective to bring the system to bring the compressor to a safe condition whenever some unsafe condition triggered for the process are in place. So that means high vibration or high temperature or even high flow. So usually this safety instrument function is encompassed by sensors, control system, and this control system will send some command for or shut down the compressor or reduce the compressor flow, or even to close some valve to eliminate the input or reduce the input to the compressor or output. Okay, or even close one line and open the other line to enable to mitigate the risk, the high pressure, high temperature. Okay, so the sensors are very important. Usually we have more than one sensor, and we have the key hour of n as a combination. That means we need to get information from at least two of the three sensors that says that the temperature achieved the threshold, and we need to shut down the compressor or reduce the compressor flow. So in some cases, such issues in the sensor are critical. So we can see, for example, lack of signal can be triggered by wrong configuration of the system. Is an issue design. So during the design, we perform some halting, accelerating tests to be sure that this lack of signal will not be triggered by the wrong configuration. Okay, and disconnection again is a wrong installation. We need to look on it. It's critical. And wrong installation, of course, we need to have a procedure to install the compressor, to install the sensor parts of the compressor. The control also have a continual signal as a failure mode here, caused by wrong configuration. Again, that's a design issue. So here we need to perform software tests during the design. So concerning the safe instrument function, we carry out some tests. So usually when we have a test or one window opportunities to that we need to make some intervention in the compressor, we also have an opportunity to make some tests in this safety instrument function. That means the sensor and the control to be sure that they are fulfill their function. Okay, and there has no failure on the demands. But let's take a look on the filter. And the filter has some critical issues here. We need to be clear that the filter do not have an instantaneous effect in case of failure in the compressor, but that's cause a cumulative damage after a period of time. If we will not eliminate the failure, the loss of the function of the filter, that will be a consequence in a compressor or even a pump. So in this case, it's a compressor, so we need to look on some critical failure modes as a blockage. So overload of the filter can cause a blockage, and this overload will cause high pressure with equipment damage, and if that's not replaced, we have a process impact. Okay, so based during the FEMEA, that's what's defined as a critical. We need to define preventive maintenance for that, and so we have a monitoring online pressure for the filter. The other critical issue are corrosion for chemical attack. So we need to make some sample products. That was the action defined during the RCM here. That will be online. The other point is disconnection by the wrong installation. So during the FMA, we already define procedures that is necessary to define a procedure to avoid this wrong installation and make some inspection after the installation and after each maintenance to avoid this problem. If we look on the compressor configuration of the filter configuration here, we have two filters. So that means we need to lose both in order to start to have impact on such a compressor. So uh, this cost of two filters can be avoided also if you have a routine of preventive maintenance in one of the filter, and that is one of the discussion that we can have during design. But we need to implement the RCM during the design in a proper time in order to have this confront of information and have this a proper discussion. Okay. So let's move to the next case study. The tank. The tank is also a critical system that is part of many industries such as oil and gas refineries, for example, petrochemical plants and pharmaceutical plants and small tanks, of course, and other process industries. So tank is very critical because it affects usually the process production, as well as there are a lot of safety related issues. So usually for its integrity safety related issue, the risk based inspection are the technique that's very similar to RCM when carried out during the design phase. That is the most appropriate one to define the integrity issue problem. But of course, during the RCM, we can define many predictive maintenance non-destructive tests, and will be the similar ones that will trigger, that will avoid or detect the integrity problem. Okay, so as a first step, we need to define the tank list of components. So for this RCM, we consider tank, vents, PSV valve, control sensor, alarm, nozzle, and gasket. So again, the first step during the FMEA is to fulfill this template here, and we have a tank with product tank. We have only one tank. That's another big issue. That's also part for run analysis, not for the RCM. But how many tanks we have will define the impact and the critical of the failure of the tank. So here we have one tank. So it's a storage tank that's very critical. That's the tank will be available whenever it's necessary. So here we have the tank's functions as we discussed during the female model, all the finance, and then we start the RCM. So here you can see that we call the R as a RBI, and that will be the same effect here because we assess the consequence and we consider here the effect of safety in terms of leakage. So let's take a look on it. We have here leakage with safety, environment, social process impact. So that's very critical in terms of consequence, and that need to be mitigated. So here is simplification of the female. We do not have the risk, but of course this leakage here are the most critical one, and that's why we have some maintenance tests defined during the RCM here. Okay, it's during our RBI, let's say like that. So we have non-destructive tests, ultrasound test, and probabilistic degradation analysis after corrosion detection. So that's a quantitative methods that we can predict when the failure is expected to happen based on the level of thickness reducing along the time. So that's the type of method that is full presented in the lifetime data analysis online training. And if you want to get more detail about that, you can take a look on this specific training. Okay, visual inspection and hydro tests in the tank. So some of these tests are defined for regulation for the law. This one is one of them that you need to carry out hydro test every 5 years. So there's no discussion about that in your RCM. In some cases, you see that as long as the tank getting older, maybe after 15 years, you need to reduce this 5 years for 3 years. And similar, when you apply non-destructive test after 15 years, it's time to detect some corrosion in the tank, so you need to reduce the frequency that you apply this non-destructive test. Okay, so in the very beginning, you need in startup point you apply some non-destructive test, and every 1 year to avoid this to be sure that there is no early life failure. And after that, you can change such frequency for 3 5 years because it's not expected to find any corrosion. But after 10 15 years, you can find something, and sometimes the product in the tank is that is specified for the tank is not respected. So in some cases, it's necessary to put products that's the corrosion level is higher than specified for the tank, and then we can start to have some corrosion earlier than expected. Is that another point that we need to be aware? And in case of that's the corrosion starting to happen before that, you use some products that have a higher level of corrosion that is specified for the tank design. We need to review this frequency of non-destructive tests. Okay, and again, in the bottom of the tank, another part that we can have leakage, we have visual inspection every 5 years. Another type of test that's magnetic flux leakage test in every 5 years. Okay, so we have another parts here that we implement the let's say the maintenance task inspection that's based on our RBI in here. That's in this case was carried out during the design test, and so have the same effect of the RCM. So for the joint, we have some worn out here that's caused by normal wear out or incorrect installation. So the consequence here is leakage with safety environmental impact similar to the gasket. So they put some radiography tests here carried out every 3 years. Monitoring online vibration, we have for the looseness, that's the failure mode of looseness caused by high vibration. So we have some monitoring vibration online to avoid that, and it's very critical. We can have a disruption of lines in a joint, and that will be a leakage as well. Okay, so we have some radiography tests also for the gaskets after installation and maintenance, and after in every 3 years. And here we can see vents and PSV valves. Okay, so fail to open is the main issue that there are cause for some internal components damage. So we need to look at the integrity of such valves and vents. So non-destructive test, radiography test, visual inspection and cleaning, online test, non-destructive radiography test, visual inspection. So visual inspection every year, and non-destructive test for the vents every year, and non-radiography test as well every year. Okay, so we need to be sure that such device that's safeguard the tank in terms of safety are always in a state as good as new. Okay, so that was the model 8 applied for RCM cases. So as we discussed during this second day of the training about the RCM, so the RCM is not a big issue as in terms of analysis. Requests that we have during the workshop, good specialists, very good specialists that are able to really understand the components failure modes and predict the maintenance tasks. And of course, after such a list of preventive maintenance tasks, we need also to link such information, the impact of such preventive maintenance tasks in system performance, spare parts, and life cycle costs. But that's another issue. The main objective here was demonstrate the RCM, how simple it is, and we give some example of pump, compressor system, and tank. And yeah, in the next model, we see how to use RCM software to implement that, and then we're going to see the advantage to have a software and the difference between applying such RCM analysis in an Excel sheet and the difference that we have by applying any kind of software. Okay, so thanks for your attention. If you have some question, just send to me. So just additional information, these case studies are in the book, my book, Gas and Oil Reliability Engineering, Analysis and Modeling, and as demonstrated in the first model in the introduction. So there are more examples about FIMEA an RCM in this book, particularly concerning equipment for process and oil and gas, as well as another type of models that you can find in there concerning female RCM and how to model and assess the preventive maintenance task. Okay, so thanks a lot. If you have some questions, just send me a message, please.